So we're going to be talking a lot about polynomials in this class, which is probably not a surprise. You started talking about them in Algebra 1. We're going to be talking about them a lot more in Algebra 2. And one of the things that you might want to know is there an easier way to evaluate a polynomial for a given value of the variable? Here's an example. What is the value of 3x squared minus 2x minus 7 when x is equal to 4? Another way we can put that is, given f as a function of x, defined as 3x squared minus 2x minus 7, let's find f of 4. That's the exact same question, just expressed a different way. So the most straightforward way to do this, of course, is simply to plug 4 into the function and for x and actually do all the arithmetic. And this is sometimes called direct evaluation or direct substitution. And this is what we usually do most of the time, right? So, for instance, f of 4 would be 3 times 4 squared minus 2 times 4 minus 7. That's going to be equal to 3 times 16 minus 2 times 4 minus 7, because we evaluate our powers first. Now we do the multiplications. That's 48 minus 8 minus 7. And that comes out to 33. So apparently, f of 4 is 33. Now, that's fantastic. As it happens, that's not the only way you can figure out what the value of this is when x is equal to 4. That's not the only way to figure out f of 4. There's another way. This is referred to sometimes as synthetic substitution. And this is a very useful technique that gets around a lot of the arithmetic problems that happen when these polynomials get complicated or the value of x is complicated. Now, synthetic substitution works for polynomials with one variable, which is what this is. This is a polynomial, and it's got one variable, and that variable is x. And we want to figure out what happens when x is 4. So here's what we're going to do. The first thing we're going to do is we're going to write down the coefficients. Rather than writing down the whole thing, 3x squared minus 2x minus 7, we're just going to write down the coefficients. 3, negative 2, negative 7. Okay. And off to the left here, we're going to write down what value we're using for x, which in this case is 4. And I'll write this off to the side like this, kind of put in a little corner. And I'm going to draw a horizontal line here. Now, these lines that I'm drawing aren't magical. They're just one way of writing this stuff down in an organized way. Now, the idea now is that I'm going to evaluate this polynomial when x equals 4 without actually having to write out any of this stuff, right? And the main thing I want to avoid is having to take my x value, which in this case is 4, to multiple powers to evaluate this, right? So the first step is we take this first coefficient and we just kind of drop it down here. You don't have to write the arrow, but I very often do. Once you've dropped down that first coefficient, and that's an important first step, make sure you do it. Once you've dropped down that first coefficient, right, you're now going to go through a repeated process. You're going to multiply the 4 times this 3 and put the result here, 12. And then you're going to add up this column. Negative 2 plus 12 is 10. And then you're going to do it again. 4 times 10 is 40, and negative 7 plus 40 is 33. We got the same result we got doing it up here. Now, this may seem like kind of, why would I bother to do this when this works just fine, right? And especially the first time you see something like this, the process seems a little arcane. This is easy to understand. I know how to plug a number into an expression, sure. But what happens if your variable is being taken to higher powers, like the fourth power, the fifth power, and you've got a lot of terms? What happens if the value you're substituting for your variable is not something nice and easy, like 4? What if it's a negative number, or a fraction, or a decimal? Let's do another example. I'm going to take the function f of x equals negative 2x to the fourth plus 10x to the third minus 9x squared plus 3x plus 2. And I want to evaluate this, let's say, when x is equal to, let's do negative 3, right? Actually, let's do negative 5. That sounds like fun. Let's figure out what f of negative 5 would be. Well, using direct evaluation or direct substitution, I would write negative 2 times negative 5 to the fourth power plus 10 times negative 5 to the third power minus 9 times negative 5 to the second power plus 3 times negative 5 plus 2. All right, that's fine. Now we're going to work on all these powers of 5. And if you know your powers of 5, that won't be too bad. But what I'll probably need to do, if I don't know my powers of 5, is grab a calculator. So here's my calculator. So, first of all, what is negative 5 to the fourth power? Well, let's see. I don't like this calculator. I don't want to use that. I'm going to use this one. So I want negative 5 to the fourth. It's not on. There we go. Negative 5 to the fourth power. If you can see this, what we wind up with is 625. So this is negative 2 times 625 plus 10 times, well, now I got to work out what negative 5 to the third power is. Negative 5 to the third power. Notice, by the way, that I put the negative 5 in parentheses so that it's clear I'm taking the entire negative number to that power. Well, negative 125. Negative 125. Minus 9 times, well, I know what the square of negative 5 is. That's 25. Plus 3 times negative 5 plus 2. So there's all my powers taken care of. Now I got to do some multiplications. What on earth is negative 2 times 625? Well, I know it's going to be negative. 625 times, times negative 2 is negative 1,250. This is going to be plus 10 times negative 125. That's also negative 1,250. This is, let's see, not minus 9 times 25. 9 times 25, I think, is 225. Yes, minus 225. Minus 15 plus 2. Okay, now I just got to add all this stuff, right? All right, so I'm just going to calculate that. Negative 1,250 minus 1,250 minus 225 minus 15 plus 2. What we get is negative 2,738. So there is f of negative 5. Well, that was ugly. Can we use our synthetic substitution process to make this easier? I say we can. Let's start by copying down our coefficients. Negative 2, 10, negative 9, 3, 2. And we're evaluating this when x is equal to negative 5. Now, the advantage of this approach is that I never have to take negative 5 to a power while I do this. It never happens. I never have to worry about it. I'm just going to do this process, and it's going to work out the powers for me as I go. Later on, if I have time, I'll explain why that happens. But for the time being, we're just going to go through the process. We remember we start by dropping down the first coefficient, -2. And now we begin this process where we multiply and add, multiply and add, multiply and add. And we keep doing this until we get to the end. And that last number we get here is the value of f of -5. So here we go. -5 times -2 is 10. 10 plus 10 is 20. -5 times 20 is -100. -9 plus -100 is -109. Now, if I don't know off the top of my head, 100, this is going to be a positive product, right? -5 times -109 will be positive. 5 times 109 is 545. Add 3 plus 545 is 548. Finally, 548 times -5, 548 times -5 is -2,740. And -2,740 plus 2 is -2,738. So I still had to do some arithmetic, and some of it was still kind of ugly, right? I still had to work out what 109 times 5 was, and 548 times 5. But I didn't have to do nearly as much ugly stuff as I did up here, right? And that's primarily because I never had to work out what -5 was to any power. All I had to know how to do was multiply two numbers and add two numbers. So remember our process, right? Our process, in general, looks like this. We have a polynomial, and it's got coefficients, and we put down those coefficients in a row. Over here, we put down the number we want to evaluate the function at. We drop down our first coefficient, and then we multiply and we add. Multiply and add. Multiply and add. Multiply and add. And eventually we get to the end, and this final number here is the value of the function evaluated when x, or the variable, whatever it is equal to that. Let's do a couple more examples. Let's work out, and again, I'm going to do it both ways, right? Not that I have to, but I'm going to go ahead and do it both ways. Let's work out what would happen if I tried to evaluate the expression 3x to the third minus 4x squared plus 4x plus 6 when x is equal to, let's do 9. We'll do 9. So let's figure out what f of 9 is, right? If this is my f of x, what we want is to find f of 9. Now, when would you be doing this, by the way? Well, maybe you're trying to graph this function. 3x to the third minus 4x squared plus 4x plus 6. And you need to know for when x is equal to 9, what's the y coordinate? That's what you need to do. That's what you'll be doing this for. So we'll write down let's do it the long way first. F of 9 equals 3 times 9 to the third minus 4 times 9 squared plus 4 times 9 plus 6. And now I have to evaluate 9 as some powers. Well, this is 3 times 9 to the third. I want to say it's 729. 9 to the third, 729. Minus 4 times 81 plus 4 times 9 plus 6. Oh, what's 729 times 3? I don't know. 2,187. 2,187 minus, this is going to be 324, right? 81 times 4. Yeah. Plus 36 plus 6. And then finally, right, I'll add all this up. 2,187 minus 324 plus 36 plus 6 comes out to 1,905. Fantastic. Let's do this the synthetic way. I'll write down my coefficients. 3, -4, 4, 6. I'm evaluating this when x is equal to 9. Now, remember the process is going to be that I drop down my first coefficient, and then, over and over, I multiply and I add. I multiply and I add. I multiply and I add. And the great thing is that once you know this process and how it's the same 2 steps over and over, it becomes very fast. 9 times 3 is 27. -4 plus 27 is 23. 23 times 9 is 207. 207 plus 4 is 211. 211 times 9 is 1,899. And 1,899 plus 6 is 1,905. And we're done. And it goes a lot faster. This goes a lot faster, right, than having to do all this. Now, there is one situation you need to be aware of. Sometimes there will be, and I'm going to put this in air quotes, terms missing from the polynomial. Here's an example. Maybe my polynomial is f of x is equal to, let's do 4x to the 4th minus 8x squared plus 2x minus 6. Now, as I do this, I hopefully will notice, right, that there's no x to the 3rd term here, right? I go right from an x to the 4th term to an x squared term. I go x to the 4th, oops, no x to the 3rd, but then I have x squared and x and a constant term. Well, if there are any missing terms here, then when you do your synthetic substitution, you need to put in a 0 as a coefficient for that missing term. So since I have no x to the 3rd term here, I'm going to imagine that I have a plus 0x to the 3rd term, because 0 times anything is 0, and adding 0 doesn't change it, right? So that means that when I write down my coefficients, I'm going to write 4, 0, -8, 2, -6. So now the question becomes, what is f of, let's do 1/2 and see what happens. Let's do 1/2. So I'll put a 1/2 in here. I think you'll like this. Drop down the 4. 1/2 times 4 is 2. 0 plus 2 is 2. 1/2 times 2 is 1. -8 plus 1 is -7. -7 times 1/2 is -7 halves. And I do have to do a bit of arithmetic here. This winds up being 4 over 2. So 4 over 2 minus 7 over 2 is -3 over 2. Times 1/2 is -3/4. And so what I wind up with is -6 3/4. Right? -6 3/4. If I add -6 and -3/4, I get -6 3/4, or -6.75. Or -27/4. Whichever way you want to think of it is fine. Now, you might be thinking, oh, but that got really ugly. Well, yeah, that was a little ugly, but think how much uglier it would be, right, if I just try to do this using direct substitution, f of 1/2 is equal to 4 times 1/2 to the 4th power minus 8 times 1/2 squared plus 2 times 1/2 minus 6. Well, this is 4 times 1/2 times 1/2 times 1/2. That's 1/16 minus 8 times 1/4 plus 2 times 1/2 minus 6. 4 times 1/16 comes out to 1/4 minus 8 times 1/4 is 2 plus 2 times 1/2 is 1 minus 6. Let me go ahead and add all these up here. -2 plus 1 is -1. Minus 6 is -7. So this is 1/4 plus -7. 1/4 minus 7, that's 1/4 minus 28/4, which is -27/4, or -6 3/4. The same answer we got up here. So anyway, I hope that's an illustration of how synthetic substitution works and why you're going to find it in many cases easier to use when evaluating a polynomial function, right, for some given value of the variable. I'm going to go ahead and give you guys more examples to work on. Your substitute, which at the time of this recording is going to be Aaliyah, will have sheets for you to practice this with. And of course, if you have any questions, we can talk about this further on Monday. Thanks very much.